Hello, today I'd like to talk about wrapping a belt or a strap or a rope around a spool or a pulley. This is all really the same thing, and the idea is that you have a spool. Here I have a green spool of radius. Let's see what the radius is. Evaluate, measure. Diameter is 4, so the radius is 2. So I've got that spool, and I'm going to wrap a green spool. I'm going to wrap this purple belt around it, and the purple belt is broken up into a lot of little segments. And those little segments I could have extended this way down, but I felt like I had enough segments here so that you kind of get the idea. And let's go take a look maybe at the very last segment, number 20. So segment 20, let's see if we can figure out how it's mated. So it's mated. There's a mate on the end. Keep the ends of the belt segments well behaved. And then a given belt segment has a mate that is just an edge mate so that it will hinge right there, and that type of thing continues up. Each neighbor is mated in that same way with the preceding one. And then I have all of the belt segments having their right face parallel with the right plane of the assembly. So that's actually an initial condition there. And that all of them have that feature. And as you work your way up to the top, you end up coming upon the very first belt segment and its edge. See, the ends are like that. And its side edge or side face is coincident with the face of the pulley. And let's see what else. Not that one. It's, again, that right face is parallel with the right plane, so we have that. There's the one I wanted to show you. So that topmost edge of the very first one is mated with a sketch that's on the top plane of the pulley. And if I were to hide this, you could see what I mean. There's actually a sketch line there, and that's what I've mated that to. Turning attention maybe next to the pulley, let's take a look at how the pulley is situated and its mates. Of course, the pulley's not fixed. One thing is I have a concentric mate of the pulley around this axis 1. Axis 1 comes about from the defining planes of the assembly. That's going to be the top plane and the right plane. So that gives me axis 1. And then I take that face and make it coincident with the front plane. So I've got a pulley, and of course I've got the two mates with the belt. And then the final sort of mate is an initial condition mate, where I get the pulley's top plane coincident with the top plane of the assembly, so that I get, yea, verily, it's fully defined. And those initial conditions, like that last one I just showed you, those initial conditions will be suppressed when we go and look at the motion study. In order to set myself up for success, I thought I would take a little peek at some theory and think about what this pulley and strap or pulley and rope machine would do. And let's think about what it would deliver. In other words, what is the rope going to be pulling translationally? Let's say I've got a 10-pound load on the end of the rope or strap, and at the end of the rope or strap is going to move at 0.2 inches per second. And I know that I can get a notion of power here by taking inch-pounds per second, and making that foot-pounds per second by dividing by 12. And then I know there's 550 foot-pounds per second in 1 horsepower, so I divide by 550. That gets me into horsepower, and I know 746 watts in a horsepower. So I multiply by 746, and now I've got my power in watts. I've got my force or my load in pounds, and I've got my velocity, translational velocity in inches per second. And I know that it's a rotary to translational machine, and I know my gear ratio is going to be 1 over the radius. And my radius, I told you earlier, was 2 inches, so I've got 1 over 2. And the units on the gear ratio is going to be radians per inch. And I said hypothetically here, let's go ahead and say 0.99 for our efficiency. And thought I would, before I go and take a peek over here at what the rotational things would look like, maybe I'll try to insert a text. Can I do this? A text box? Let me see if I can do this. Insert a text box, and then I'm going to try to insert maybe an equation. Oh, good Lord, I can. How about that? And maybe I can make it a scotch bigger here. Something like that. And I do know that gear ratio is equal to input speed, which in this case, I need to be thinking in terms of omega sub I. I need to be thinking in terms of radians per second. And the output's going to be inches per second. So I can rewrite this. I want to know what the omega is. Try this again. And I'm going to say, okay, omega. I want to know what the omega, I actually want to know what it is in RPMs, but we'll get there. G times V naught. So I know I have that. So basically I've got G, the G I have here, being defined as input speed over output speed. And I'm going to go ahead and rewrite it in terms of V naught. I'm sorry. Yeah, so I'm going to get omega I in terms of G and V naught. So basically multiplying through by V naught. So I know I got that over there. And then this is going to be radians per second. Let's see what I've got over here. All right, so I do I7, right? So that's V naught times F6. That's my G. And then since that's going to be radians per second, I want to divide by 2 pi so that I get revs, and I multiply by 60 seconds so then I get per minute. So that looks like 0.955 RPMs. And then I know that mechanical advantage, I'm going to insert another equation. Check this out. Guys, getting the hang of this. So I know mechanical advantage is eta times G, and that's going to be output load divided by input load, which I'm using the subscript R for rotation, I guess. But anyway, so I want to know what is TR. So I can insert yet another equation. You guys like equations, so FO divided by eta G. Go back in here and sneak a space in there. Make my text box a little bigger. So anyway, that's not too bad. So yeah, let's go take a look at my TR. So TR is going to be I6 FO divided by F6 times F7. Boop, boop. Yep, so it looks good. And if I were to show maybe, yeah, if I showed more digits, it's not going to be exactly 20 because I've just got under 1 for an eta. Anyway, and then I go and do some a little bit of discipline here, which you guys have done. I'll take inch-pounds times RPM, and this 5252 gets that RPM, helps get that RPM in terms of radians per second, and the 12 is to get that inch-pounds into foot-pounds, and the 746 is to get you into watts. I always like to do this. I'd say, okay, I want to look at the output, power divided by the input power. And you can see that the output is just a little bit less than the input. So everything's looking pretty good. And I said, well, I'm just kind of curious in degrees per second what that is. So I took that C7 just to get a feel for how to run my simulation, how long to run it. So this all looks pretty good. So what I'm going to do is I'm going to move the input. I'm going to move the input with a Solidworks motor, and I'm going to load the output. Right? So these are going to be set, and load the output with the 10 pounds and move the input at 0.955 RPMs for a certain period of time. I think I did 8 seconds. And then I'm going to do a plot of the output speed. I'm going to do that in green. That's a good green there, isn't it? So I'm going to do a plot to show, yea, verily, I get 0.2 inches per second. And then I'm going to do another plot of motor torque to show, yea, verily, it's about 20 inches per second. If it's off a little bit, it could be that, this 9.9 is not quite right. So anyway, let's take a look. Okay, let's take a look at the motion study that I created. And I created, using a motion analysis, I created an 8-second motion study. I have a rotary motor that is turning the pulley counterclockwise from this view so that the belt would wrap as we desire. I applied a force. Oh, go back, take a look at the motor, see how fast it was going. So applied that motor at, like we talked about, 0.955 RPM. Okay. Then I applied a force at the end of the rope, like that. And I think, to be honest, applied it right, I think, to that edge. Applied it to that edge to keep all the edges under that load, and I applied it in the direction of that face. And I put 10 pounds. So I'm set up to move. I'm moving the input and loading the output. And then for solid body, I picked all bodies in this, the spool and whatever wrapping around the spool. I picked all of those and put them all in the same solid body. I've never tried this. Number of contact pairs, 210. I've never tried this. Gutsy call. And here, set it all up for steel dry. So, and then I went down to the mate area, and a lot of the mates, like the concentric around the axis and coincident with the end faces of these things, I'm keeping those active. As you can see, they're active throughout. The ones I'd mentioned to you earlier that are initial conditions, like the pulley top plane and then all of the parallels that you see as I'm moving down here, those are all suppressed. The parallel, the right side faces being parallel to the right plane. You can see here they're all suppressed. So I think we're ready to go, and I calculated. And one thing that I want to point out to you as it plays, I actually created this is my initial view. I created a different view to finish it, which looks like that. Okay, and what happens is during the motion study, when it replays it, it'll feather between those two viewpoints. It's pretty nice. It doesn't affect the motion study, just gives you sort of a changing view, and I wanted to show you that in case you wanted to try it. But let's play it from the start, kind of see what it looks like. You can see the belt wrapping around the pulley, just like we think it should do it. That's so cool. And what I could do first of all is take a look at the plot of velocity. So this would be output velocity. And I think we were looking for about 0.2 inches per second. Let's take a peek here. Yeah, we're looking at the 0.2 inches per second. And yay, verily, that's pretty much what we have. It's pretty awesome. Kill that. Let's go take a look at the motor torque, show plot for motor torque. And that looks like it's about 20 inch-pounds, give or take. Pretty smooth, actually. Let's see what we're supposed to have. Right at that 20. It's maybe a little higher. It's kind of showing me it's either right at 100%. Looks like it's right at 20. So I'm pretty happy with that. I mean, we could, even within Solidworks, we could kind of take a really closer look here what's going on. Let's take a peek. 19.5 going to 20.5. Let's see what that does. A little undulation there. It looks like it's about 20.5. 20.5, and we're looking for about 20.2. Wow, that's amazing. So to put it into perspective, what we have here is we had certain delivered variables we had that we wanted, and we had a model for our machine based on gear ratio and efficiency, and we predicted what the input torque and input speed would be, and then we used SolidWorks to prove that this theoretical model was correct. So I think that's a pretty cool thing. Go back to the SolidWorks. Just play it for you one more time. And you know what I could do is even show you how to save an animation. Let's see if we can do that. So I'm going to save assembly 1 AVI, save it, see what happens. I'll just keep it like that. So play it one more time and I'll save it. Cool. See if we can find it now. Okay, here we go. It's right there. Let's see if we can play it. Oh, there it is. Very nice. See the belt wrap around the pulley or spool. Very nice. Hope you've enjoyed it.